Welcome to Computer Science and Engineering 120, Learning to Code. This is Module 2, Introduction to Data. In this first part, we'll be looking at working with data. In particular, we'll look at several data formats and several data operations that can be performed on data. Data models real-world problems. Data is used to make decisions and learn information. Understanding data is necessary to give us insights and further our knowledge. As an example, consider the following pieces of data. This is enrollment data for particular students enrolled in particular courses. The format of this data is as a table, which is nice and easy to read for humans, but it's difficult for a computer to process. It's difficult to manipulate, and moreover it's static. There's no real way to discern any patterns or statistics on this data beyond individual records. Now consider the same data but in the following format. This is called a comma-separated value file. It's essentially a flat file. It's not really intended for human consumption, as it's difficult to read and it's difficult to parse for a human. However, this format is much easier for a computer program to process. Now it knows where each piece of data begins and each piece of data ends. However, it still lacks sophistication. We still have the same problems of not being able to make sense of the data without further processing it. You could represent the same data using a spreadsheet, such as Excel. For example, here's the same data represented in Excel. Spreadsheets provide a means to manipulate and process data that we didn't have before. Unfortunately, the data is tied to a proprietary format. The Excel file would only be able to be opened up in Excel or a program that understood that format. Also, the operations are limited to the functionality that the program provides. As an alternative, consider the same data in a different format. Here we have XML. Extensible markup language, in which each piece of data is marked up using a tag beginning and ending with angled brackets, along with a name for the piece of data that represents what that data is. It's an open, standardized format. It's interoperable. Pretty much every programming language is able to support XML or has a library to do so. Each piece of data is marked up with a tag giving it semantic meaning. For example, we know that Starlin represents a first name because that's what it's been tagged with. Moreover, it has a tree data structure. The roster has various children tags called enrollment tags. Each enrollment tag represents an individual student and an individual course in which they are enrolled. This defines a parent-child relationship that's extremely easy to parse and work with. Here's the same piece of data in JavaScript object notation. This is the format that we'll be working with mostly. It's also open, standardized, and interoperable, but it's more lightweight. There are fewer characters needed to represent the same data, resulting in less storage and quicker transmission time when sent over a network. It also has the same basic tree data structure. The data is stored as key-value pairs, and it's a subset of JavaScript, so it has the advantage that it can be used directly in the JavaScript programming language. Regardless of the format in which we store our data, there are several data operations that we can perform on it. The simplest being electronic data interchange, or EDI. This is simply transforming the data from one format into another. For example, translating or transforming the data from a CSV file into XML so that it can be used in a different programming language. Or exporting our data from Excel to a JSON format so that it can be used in a JavaScript application. EDI facilitates communication between two different systems, so that one system that's written, say, in Java or a completely different framework can talk to another system that's written in a completely different programming language. More sophisticated operations would include data organization, such as sorting. There are various ways that we could sort this data. We could sort it by student to generate a class listing for each student, or we could sort it by GPA to find the top students or to find the students that need more help. Or we could sort it by course so that we could get a roster for the instructor of each course. Once we have data, we'll of course want to search for particular records, for a particular student record or a particular course record. Two major issues in either one of these operations is efficiency and scalability. Both operations could be very quick and easy to perform on small pieces of data, but may not scale well when we've got millions or even billions of records. Another way to organize data is data normalization, where records would be separated out into different tables. For example, we could have a student table and a course table. In our original data, each student record had a lot of repeated data. For example, the name was repeated for every course that they were enrolled in. This is highly inefficient, and we might want to normalize it by creating one table to hold student data and another table to hold course data, and then make relationships between those pieces of data. This is typically done in a relational database management system, which is beyond the scope of this course. You can also do data aggregation, where you can bring pieces of data together to form new information, such as computing various statistics. How many enrollment records do we have? What's the average GPA, etc. We might also be interested in the total number of enrolled students in each course, or the total number of courses, or the average number of enrolled students in each course. We also might need to group the data. For example, what if we wanted a total number of credit hours for each student to ensure that they weren't over-enrolled or under-enrolled? Or we might want a total enrollment count for each class to make sure that each class wasn't over or under-enrolled. This would require grouping data according to either student or to course. Another way that you can work with data is to do data visualization. Computers are very good at processing large amounts of raw data, but humans aren't. Conversely, computers are not really good at recognizing patterns, but humans are. By visualizing data, we can make it clearer to a human user that can immediately spot various patterns. This could be as simple as a bar graph or a pie chart, or more advanced techniques like designing a heat map or connection graphs. Finally, a more advanced technique is data mining. It involves data mining and machine learning. These techniques can be used to discover structures, patterns, and information that you may not even realize that you were looking for. They can be used to create models and make predictions using clustering and various classification techniques.